I'd like to thank you all for getting up so early on a Saturday and coming down to the USC. It's going to be well worth your time this morning. So without further ado this morning, I'd like to introduce Tom Campbell.
Today is going to be a really busy day. It's going to be a lot of information. I use the analogy, it's going to be like drinking from a fire hose. You're going to get lots of information, and it'll be hard to process all of it, but in time it will process for you. Again, the slides are available to you at the My Big Toe, www.mybigtoe.com. They're there now. The slides are busy, but that will give you at least a little bit of recall of what was said and what we talked about if you go there. First, before we get started, I'd like to calibrate the audience with a few general chunks of foundational understanding. One, we'll be talking about evolution and then about various levels of evolution as we as individual units of consciousness evolve. Some of us are more or less evolved, but I want to make that clear that that's not some of us are better or worse. Some of us are just different. They're more evolved or less evolved. Don't take that with your ego to think that, oh, I'm more involved than somebody else, or they're more evolved than I am, or whether you decide you're low or high on that scheme is not helpful. Don't consider yourself either way. You just are who you are, and they are who they are, and all of us are struggling with who we are and what we have to work with. We're all trying to learn. And all of us are in the process of pulling ourselves up with the bootstraps. So just kind of respect and have reverence for everybody, even the ones that are obviously struggling more and maybe have more fear and more ego than is healthy for them or the people around them. Everybody's just doing the best they can. Okay, we're all just doing the best we can with what we've got. So if any way you can be helpful to another person, to help them grow, then do that. But let's not get into the hierarchy of who's higher, who's lower sort of thing. So that's something to avoid. Spirituality, personal growth is really a different thing than out of body and the paranormal. They are connected, but the out-of-body and the paranormal experiences are not a prerequisite. You can grow just as far as you can without ever doing any of those things. So don't get frustrated as I can't do this. That's not the case. If you can't do paranormal things, that's not a big deal. It's like, so what? What you can do is grow the quality of your consciousness. And that's what's important. Matter of fact, most of the people who get frustrated at not being able to experience paranormal things or do out of body, they get frustrated because they're trying so hard to do that and because they're not quite ready yet for that part of their experience. It's much more productive if you get yourself ready, which means focus on getting rid of your fear, focus on letting go of your ego. If you can focus on those things, that every choice you make during the day is a choice of caring. It's about others. Then the paranormal things that are very attractive, and a lot of people say, I want to do that, that's exciting, I really want to do that, then those things will come along on their own. But toward the end of this day, I'm going to teach a little bit about remote viewing and a little bit about healing with the mind, because those are evidential things that you can do and then check up on it to see whether, did you actually do that? Did you get that remote view target right? Is that person actually getting better? And you need to do that for a long enough time that you get convinced that what you're doing is actually having an effect, that it's real. It's very important to get that evidence. Growth that we're talking about is always at the being level, not at the intellectual level. So if you happen to be a right brain person and you really don't do intellectual, logical process isn't your thing, you just kind of get it at a right brain level, that's fine. That works just as well. You don't need to use your intellect to get there. The intellect can be helpful, but again, it's not required. Meditation is a tool, not an end goal. Okay, it's just a tool to use to help you focus and get rid of the noise. I'm going to break some of your favorite paradigms. I'm going to run over a few of your beliefs. Please just remain skeptical and open-minded. You know, if you're skeptical but not open-minded, you may catch yourself in a trap. That trap is called a belief of self-omniscience. Okay, but that says if I have not experienced it, then it cannot exist. That's the same as saying, you know, I know everything, right? That's omniscience. That's what happens if you're skeptical but not open-minded. And that's a trap. There's another equal trap that if you're open-minded but not skeptical, then you fall in the trap that says, I believe whatever I'm told. You have to be skeptical. You can't believe things even just because they make sense. We all know about illusions and mirages and things that we see that we can get convinced they're real but are not. So you always have to be skeptical. That's important. Never take anything as, well, I shouldn't say never take anything, but take very few things as true and false. Take things as probable or not probable. Well, I think this is 99.999 probable that this is the way it is. But leave that little bit of uncertainty in there so that you can still learn. If you don't have that uncertainty, if I know this is it, then you're done. You no longer go back and you'll no longer go back and sample that data. You'll no longer have any questions of, well, is there anything else that tells me differently? So try to avoid the belief and the disbelief. That's a high risk way to go. It's almost impossible to have all the information to come to a logical conclusion about anything important. If it's really important and it's really significant, we almost never have all the information we need. You know, think of all the things in your life that are really important, you know, to you, that are significant, and you'll find that all the information is just not there to make a logical decision. Logical decision is if this, then that, if that, then this, and you end up then with therefore and a conclusion. That hardly ever happens to us. We always make assumptions. We're always guessing at what the data is. And when we do that, we need to keep in mind that we should be skeptical. There may be more data, and that we should be open-minded. There are people that are convinced that men never went to the moon. All that was somehow staged, you know. So if you can't convince somebody of something that, fundamental, then, you see, it's because they don't have all the data. You don't have all the data on almost anything. If you think of anything you believe, you will find out that it's based on an assumption. You're guessing. You don't really know. There's almost nothing that we really know. And I guess a corollary with that is that anything can be explained with a conspiracy theory. If you've got something you'd like to explain, you can explain it that way. All you have to do is convince yourself that the outside world has conspired, for this to come about, and there it is. Now that may not be, it may not be rational, it may be pretty silly, but then people get into pretty silly things that way. So that's why conspiracy theories are so plentiful, because it explains everything. If you can imagine something you'd like to have an explanation for, like, I don't know, why you have the job you have, or why your boss doesn't like you, or why don't have a higher salary, or all kinds of things. You can find all sorts of ways to blame that on somebody else. That's your conspiracy. Yeah, it's not your fault. That's the conspiracy theory. And they're very popular because it makes the person who can blame it on somebody else free of responsibility. Okay. If you're looking for me to give you an objective physical proof of the non-physical, okay, that's not going to happen. I cannot give you objective physical proof of anything. Can I help you experience, say, psi phenomena for yourself so that you can come to your own conclusions? Yes, I can do that. Can I teach you how to affect physical things with your mind? Yes, I can do that. But you absolutely, objectively and conclusive, have to prove the reality of these experiences to yourself. Okay, and you can do that. Will your experience serve as proof for anyone else? No, never, just for you. So you see, that's why it has to be your truth and your experience. If you don't gather your own data, learn your own lessons, all you're left with is belief and faith, and neither can help you evolve the quality of your consciousness. So just consider the possibilities, assess the probability, and use open-minded skepticism. I want to very quickly summarize where we are now in physics as far as ideas go on a larger reality. We have Friedkin, who started the digital physics movement in 1992. That was like 60 years after the double slit experiment. It's a long time. Now the idea that our reality is a virtual digital reality, and that reality is basically informational, that is being considered in physics departments all over the place, because digital physics is kind of caught in. It works. It's a better way of approaching it. Bostrom, a head of department at Oxford, he's been spreading that same idea. Brian Whitworth has now published a series of papers. The one that I have here is just one. He produced this first paper that was about the physical world as a virtual reality and came to the conclusion that that's a much better physics to make that assumption. And since that time, he has published papers called Simulating Space and Time, Light, and then the next one that's coming out is going to be Matter and Movement. So he's taking it to, he is deriving the equations and mechanics of physics from the ground up, basing them on virtual reality. So see, it's moving along. Things are happening here. However, neither Friedkin, nor Bostrom, nor Whitworth, nor the dozens of others at universities who see truth of the fact that we're living in a virtual information-based reality would dare to expand their scope to see a big picture that includes metaphysics or the paranormal. At least they wouldn't do that in public. Not if they want to remain respectable among their peers. So they're going to be working this virtual reality just on the angle that it explains physical reality. They won't go any farther than that. Yeah, academia is not so open-minded as it claims. Okay, big picture scientific model. We're going to talk a little bit about models, big picture and little picture. I guess by now most of you are familiar with the terminology of big picture, little picture. Little picture describes how things work, not why things are. Science interest is the interactive and causal behavior of the objective stuff. The objective stuff is what has small uncertainty. Okay, if you think of all the things that physics, the hard sciences do, they all deal with things that have very little uncertainty. They're dealing with the stuff. Some things that are objective are like size of a rock, does a roof leak, where are your car keys, is the door locked, the brand name of your clothes, your car, is the gun loaded. These are all objective facts. Okay, things that can be measured. Subjective things would be like meaning, significance, point and purpose, right and wrong, morality, value, justice, beauty, love, caring, compassion, fear. You know, should I marry this person? Should we have children? Should I fight or take flight? Is lying in this situation wrong? Intuition, guessing, all things that cannot be measured. All of these things are things that can't be specified, can't be measured. Relationship, morality, significance, value, choice. You see, this is the subjective things. Now, out of those two lists, which is more important to your life and to your growth? See, it's not the facts that really matter so much. Now, the facts may matter on your job because you may have a fact-based job, like physicists, and scientists, and automobile mechanics. They have fact-based jobs. But as far as your growth, your life, what's significant, your relationships, your family, these things all fall under subjective. The point is that though the facts of objective reality are important, they're not the only thing that's important. Okay, big picture models have to describe everything, objective and subjective. And to be valuable, a big picture model must do better physics and better metaphysics. Okay, now we'll look at physics today. Little picture science holds the opinion that there is no larger causality, that the stuff is all there is, and we're basically just part of that stuff. But it also says that physics just is. Physics, our reality, starts with a big bang out of nothing. Okay, that sounds like a mystical belief, doesn't it? Reality just starts out of nothing. There was a big bang, and then there was the tight, packed energy that expanded, and we end up with this universe of ours, and we end up with our sun and our planet and us that evolved from all of that. Well, the Big Bang had to have some cause, did it not? It had to have some origin of its own. But that origin, you see, cannot be in this universe. It cannot be out of this physical universe because the physical universe didn't exist until after the Big Bang banged. So how did all that energy get wadded up in that little ball? How did that happen? Where did that come from? You see, now, physicists feel that that's science, but yet it's just obviously a belief. It's a belief, as they say, that's non-falsifiable. That's not really science. It's a scientific belief. The interesting thing is that there is only one way only one objective thing you can do, that I know of anyway, that will verify that we're living in a virtual reality. The one thing that will verify a virtual reality is that the virtual reality, you see, is called virtual as opposed to the actual reality, which is where it's being produced. The computer that's producing the virtual reality has to be in a different reality than the virtual reality. Your reality has to come from a source other than itself, because a reality can't cause itself. Okay, you can't be your own cause. So the way to tell a virtual reality is that you try to follow back the cause of where did it come from? Where did it first exist? And if you're in a virtual reality, you'll always get to an endpoint where there is no answer, because it actually existed when somebody in the computer room hit the run button, right? That's when it existed. But that computer and that run button have to be outside of the virtual reality that's actually running. And when I say outside the virtual reality, I mean if you're a character in that virtual reality, what you do and see in there is what's defined as physical, right? That's physical in that virtual reality. That computer room and that button is non-physical. It's not in your reality frame. It's in a different reality frame. So the way to tell you're in a virtual reality is you'll get to that point of where did it all start, and you'll hit a wall that you can't go any further because the start was outside of your reality. Sounds like exactly the predicament we're in now, right? We start with the Big Bang, and the Big Bang, where'd that come from? No way of knowing. It just must have been in some other reality, because our reality didn't exist until after that Big Bang, you see? So is it physical? Is that place where that came from a physical place? Is it a non-physical place? Well, that's a word game. How do you define physical and non-physical? The way I define them is a simple way, and that is if it's in this universe, our physical universe, we call it physical. If it's not, then it's not physical to us because this is our physical universe. So if it's not in this physical universe, if it's outside of it, it's not physical to us, it's non-physical. That seems a very simple way of doing it. Now, scientists who get to that same point, there's a few scientists who have a many worlds view, but they cannot bring themselves to say that these other worlds are non-physical. They say these other worlds are just other physical worlds that aren't physical to us. But that just makes them feel better, you see. It's just a way of defining words. It's not really a meaningful distinction. It doesn't matter whether you call all these reality frames, they're all physical, or they're all non-physical. It's irrelevant. It's just a semantic issue. So in my lexicon, if it's not physical to us in this virtual reality, then it's a non-physical thing. So our science, with its Big Bang theory, is telling us that we meet the test criteria for being a virtual reality. Now I want to talk a little bit about models. There are a lot of reality models. Religion provides a reality model. Most people have a reality model in their head, whether they have intellectually set it aside and called it that or not. The basis of that reality model is mostly just cultural belief, things that you believe just by being in this culture, you pick it up. Most reality models are not complete, nor are they fundamental. Okay, you experience reality, translate that experience into a model. Know it or not, you do have a reality model. Your notion of reality, my notion of reality, scientific and religious notions of reality all represent reality models. Okay, there's several ways we describe our models. One, the logic of interaction, rule set, math. That's one way we describe models. Another way is metaphors, symbols. Things like strings, as in string theory, just a metaphor. There aren't really strings out there, right? We just say that because that's kind of a neat way of saying it. Higher self, chakras, these are all metaphors. And slogans, things like you get what you need and deserve, God is love, we're all one, these are all slogans. These are the ways we describe our reality models. Some models are rigorously logical and some are more descriptive and poetic. Don't confuse the math, the rules, the interaction logic, or the metaphor, or the slogans that we use to describe reality with reality. So that's a thing we tend to do. All of our conceptualizations, including scientific ones, are just models. The problem is we have these models and then we tend to believe that the models are reality. We don't understand the difference between the model of reality and reality itself. There's a big difference. Don't confuse the model with what's being modeled. They're not logically equivalent, they're very different. A less abstract way of thinking the same thought is don't confuse the map with the territory. Now that's easy. We say, well, here's the map, there's the territory. Okay, the map is not the territory, it's just a description of the territory in symbols, right, and lines. Okay, well, we have to not get in that trap. Okay, there's a difference between the effects of something and the thing itself. Our physics models things by their effects. Okay. And they do that from the data gathered by measurement. We measure the effects of an electron, and then we infer an electron from the effects. The electron becomes a part of our model of reality. Okay, so now I'm telling you that electrons, okay, we have all the sound system, it's all electronic. We depend on electrons, our lighting system. I mean, all of basically a lot of what we're doing here depends on those little electrons, right? And we can manipulate them and make them do what we want they make light, they make sound, they make recordings, they're doing video, they're doing all sorts of things, and yet they're just a model. See, but we tend to believe that that model is real because we can measure the effects of electrons. The electron is a model. It's a thing we model. Now, when I was in high school and even beginning in college, the model of the atom was like a basketball with a little BB flying around it, right? That was the model of the atom. The electron was a little BB and it was circling around the nucleus of the atom. Okay, that's called the Bohr atom. That's what they thought an atom was. Now, that was our model. What's our model today? Well, if you look in a modern textbook, even at the elementary level, you'll see a nucleus, and then you'll see this fuzzy cloud. You won't see the little BB around there. It doesn't exist anymore. We got a new model now. It's a probability distribution. It's a cloud around that atom. So see, do electrons really exist? Well, we can measure the effects, but even the common electron, which we depend on so much, it's just a model. Don't confuse the model with the reality that the model's modeling. They're two different things. It's a subtle point, but it's a very important point. Another way of saying a similar thing is don't confuse the data with the source of the data. Now see, that gets us into consciousness. You as consciousness receive data. Then you have to interpret that data. When you erroneously think that the data is the thing, you end up with an objective physical reality like this because you make things out of the data that you get. You say, well, there's the source of the data. You know, I see that thing there, and that's the source of the data. Don't confuse the data with the source of the data. Don't confuse the measured effects of a thing with the thing itself. It's a very common error. Okay. We're going to talk about the search for a toe. Some basic conflict between relativity and quantum mechanics. Just a little bit, we're going to go back to that double slit. Einstein generated the theory of relativity in and around the same time that Bohr and Heisenberg and Schrödinger and others, Planck, were devising quantum mechanics. They both came up at around the same time. Okay, and this was in the early 1920s is when all this was happening. Okay, 1915 up to about 1925, 1930 is where these things were just coming together as new science. Okay, before then, the concept of reality was completely Newtonian. The first bullet here is basically a description of Newtonian worldview. Objects exist locally, independently, within an absolute space and time. Okay, that's an objective reality. Now, that comes in two parts. First part is objects exist locally and independently. Second part is within an absolute space and time. What happened is that relativity agreed with the first. Relativity says, yes, objects exist locally and independently, but space and time are not absolute. Quantum mechanics said, oh, objects don't exist locally and independently. They're probability distributions, but space and time is absolute. You see, so each one of those sciences agreed with half the definition of an objective reality and refuted the other half, but they picked opposite halves to agree with and to refute. So each one of those sciences refutes the thing that the other science, relativity and quantum mechanics, each one of those refutes the tenet that the other is built on. So they're in basic fundamental conflict with each other. What's happened here is that each one, in order to gain a new look at the world beyond the Newtonian model, had to drop one of the tenets of objective reality. But in order to still make sense, they had to keep at least one of the tenets of objective reality so that their results that they calculated at the end of the equations were objective. So they're kind of half objective. So you see, how do you get an advancement in science in those days, in the 20s? What made the big advancement? Throwing away half of the definition of an objective reality. Okay? So you had two sciences, each one threw away half of the definition of an objective reality. Each one saw a whole new brave world out there that was very different than the Newtonian vision, but each one could still compute an objective result because they were hanging on to the other. So that's what happened. It kind of makes you think that, well, maybe the right answer is to drop both of the tenets of an objective reality. Then we would have something that would contain both relativity and quantum mechanics. Now, we've only talked about quantum mechanics, but I should maybe tell you a little bit about relativity too, because relativity also says that we do not live in an objective reality. Einstein made the assumption that light was constant. Light speed is constant, and that's not a small jump. Nobody believed that that could possibly be true. At the time, that was a silly assumption, and it created a lot of silly logical results. What that created was, instead of living in a three-dimensional reality, X, Y, and Z, right, 3 dimensions, and time, one of the results of relativity, of assuming that light is a constant speed, was that now we live in a 4-dimensional reality, which is X, Y, Z, and T. But that's different because X, Y, and Z are functions of time. Position is a function of time, and time is a function of position. So now you have a four-dimensional reality of space and time that's called space-time. Okay, and these are the logical consequences that fell out of that. If you go very, very fast, 3 strange things happen. As you approach the speed of light, say you're in a rocket ship and you're going faster and faster, as you get closer to the speed of light, your rocket ship gets heavier and heavier. Mass goes up. The mass keeps getting greater and greater until when you reach the speed of light, your mass is infinite. The length of your spaceship, say, is this long. As you get faster and faster, closer to the speed of light, your spaceship gets smaller and smaller and smaller and smaller until when you get to the speed of light, it disappears altogether. And the faster you go in this spaceship, relative to the speed of light, the slower time goes by. It gets slower and slower and slower. So if you had 2 identical twins, one of them got on a spaceship here on Earth and launched off into space, went 8/10 the speed of light for, a couple of light years, and then turned around and came back, landed on Earth. He'd step out of his spaceship and he'd only be maybe a day older, and his twin brother would have already died of old age. He'd be maybe talking to his grandchildren who would probably be older than he was. You see? So that's what Einstein said. That's the theory of relativity. That's special relativity. General relativity added gravity to that mix. But in any case, see, that tells us that reality is not objective, because in an objective reality of Newton, that can't happen. Okay, now that's why we have this speed limit that says no massy particle can ever go as fast as the speed of light, because you have all these problems. But we know that these things actually do happen because they're all measured. Einstein's theory, all these strange things have been verified by experiment. In a cyclotron, where you whiz particles around very quickly, they have to change the way they pulse the magnets because the particles keep getting heavier and heavier the faster they go. They take an atomic clock, which is basically an atom that oscillates at a very high frequency. They put it on a satellite, spin it around the Earth a whole bunch of times, and then when they bring it back, guess what? It's lost time, because they match it with another exactly duplicate piece of cesium that oscillates at the same frequency, and sure enough, the clock that's going around comes back younger. It loses time. So all of these things, though they were seen ridiculous at the time, one, the idea that light would be constant, what that means is there's constant. See, everything else velocities add. If you're in a car and you're going 10 miles an hour and you have a ball in your hand, you reach out the window and you throw that ball at 10 miles an hour forward, the instant it leaves your hand, that ball's going 20 miles an hour. You're throwing at 10, the car's going 10, it's got 20 velocities add. Not like that with a light. If you're in this rocket ship and you're going 90% the speed of light and you turn on your light, that light beam goes out at C, not C plus, not 1.9, not faster. If you're going backwards and you shine your light, in the opposite direction that you're going, it goes out at C. Doesn't matter how the platform in which the light's on, it doesn't matter how that's, how fast that's going. It's just a constant all the time. So physicists today took Einstein's, assumption and said that's ridiculous. Velocities have to add. They just have to, because in an objective reality they have to. But Einstein said, I don't think so. And he came up with that. It was just theory. He didn't do it from an experimental approach. And then, of course, he came out with all these strange logical conclusions about things getting smaller and things getting heavier as they speeded up. And everybody thought that was ridiculous, and until they found out that it was actually true. So that's the relativity side. So you see that both of these, you've seen the double slit experiment before, and you see that both of these new branches of physics, and now all of physics is really relativity and quantum mechanics. See, quantum mechanics derives Newtonian mechanics as a special case. So both of these stepped one step away from a causality that described Newton's causality, objective causality. Took one step away from it, but didn't make the whole trip. And what we're going to do is we're going to see that if you do take the whole trip away and you drop both of Newton's tenets, what do you end up with? What is it that does not have objects exist locally and independently and does not have absolute space and time? There's only, what kind of reality could that possibly be? Virtual reality, data, right? That's the only solution. So now we're seeing that physics is telling us that's where we're going. All right, so I'm going to do the double slit experiment. You've heard this before, although it's hard to understand. I think it helps sometimes to do it again. All right, the way this works is that back in the 1800s, I think it was Michelson, others that worked in optics, found that if you put light through a barrier with two holes in it, you got a diffraction pattern. The light spread out into little dots where you had the most of it here, a little less here, a little less here. And the reason they said that this happened is that the light wave, which is a coherent light wave, got here, and some of the light would go through here, which made it an independent source of light, and some of the light would go through here, which made this an independent light, because you illuminated this whole area. So you had two sources of independent light now, and these two sources would interfere with each other because the distance from here to here, from the top slit to this point, is a little shorter than the distance from here to here. And when that difference in distance turns out to be some integral number of whole wavelengths, then the waves are, one's right behind the other, they're called in phase, and it looks like this. It's like these top two, because they're just one wavelength behind. So the two humps get together, the two dips get together at the same time, they add. When they add together, then you get a spot of light. Now what happens here in the middle between all these spots of light is that's where the distance between these two paths is some odd integer of half wavelengths. Like it's only 1/2 wavelength between them. That puts them just out of phase. Or 3/2 wavelengths, or 5/2. You see some odd integer, so there's always just a half wavelength. And that gives you these bottom two. So now this hump occurs at that dip, and this dip at that hump, and they cancel each other out. When they cancel each other out, you get nothing. You get darkness between all those spots, see? So that's how it worked. Light was a wave, and Any wave works that way. We could send water wave against two holes in a dike, and you'd get the same thing. You'd get a diffraction pattern out here from the water waves. It's just a wave function. And that had been known for decades. And then Einstein did some research with photoelectric effect, which is where you hit a substance with light, and electrons get released. And he found out that light comes in discrete chunks of momentum. Well, that's the definition of a particle. Moving particles are discrete chunks of momentum. So now Einstein, not only had he said something ridiculous once and it turned out right, but now he said something ridiculous again and he said, light's a particle. It comes in discrete chunks. And of course, the photoelectric effect showed that light was a particle. His science was good. So now what are we going to do? If light's a particle, we expect that light comes and it hits these two slits. A particle is going to either go through one slit or the other, and it should make a spot here, or it should make a spot here, because that's what particles do. They travel in straight lines unless affected by some external force. That was Newton's second law. So they had this problem now. Light's a particle and light's a wave. They called it duality. And they eventually ended up saying, oh, it's both. It just depends on how you look at it. It's a wave and a particle. Well, that's a pretty cheap explanation, isn't it? That's an explanation of somebody that really doesn't know. So the explanation is duality. But no doubt, duality was written in all the physics textbooks for decades afterwards. That was the official explanation. It just happens to be both. Depends on how you measure it. Well, they decided that the way to test this was because when you shine a light like this, you're shining literally billions and trillions of photons on that all at the same time. So you have whole lots of particles. And they said, well, there must be such a particle jam at these little slits. Something's funny going on here with these particles, and that's why it acts like a wave. Of course, that turned out to be wrong. They said, what happens if we just fire one photon at a time? If we just fire one photon at a time, certainly it'll act like a particle then. Well, they fired one photon at a time, and at this slit, and they got a diffraction pattern, one photon at a time. How could that happen? How could a photon, and none of them actually, there was a dark space right behind the slit, which, shouldn't have, there's a light spot right behind the slit, which shouldn't have been, because it should have just been two on either side. So they had this diffraction pattern going on, and they didn't understand why that could possibly be that way. So they decided then to detect what was going on at those slits. These little red things are detectors. They symbolize detectors. So let's detect what's going on at the slit. And when they did that, they detected every time a particle went through the slit, they got a spot there, and every time it went through that slit, they got a spot there, and they finally got what they were expecting to get in the first time. Light goes through a slit, a particle goes through a slit, it makes a little spot right behind the slit. Well, now, that was surprising. So when they didn't have the detectors, they got this. When they had the detectors, they got that. Obviously, it's those detectors. When they turn the detectors off, they get that pattern. To put the detectors on, they get this pattern. But they also found out that if they didn't turn the detectors off, but they just let the detectors detect, so the detectors were doing whatever they were doing to detect that, but they didn't collect the data, they'd get this pattern. And they realized that it didn't have to do with those detectors at all. It had to do with whether or not they collected the data. If they collected the data, they'd get these two spots. If they didn't collect the data, they'd get a diffraction pattern. And then they found out it really didn't even matter whether they collected the data, because they did collect the data and then erased the data. And when they collected the data, here's all the data. They didn't look at it, they just collected it on whatever they collect data in a machine, and then they delete the data, then they get a diffraction pattern. So they found out what was really the key was that information. If you had the information available, in this reality frame that told you that it was a particle going through a slit because you measured which slit it went through, then you'd have to get this. You'd have to get the two spots. If you didn't have any information telling you, and it doesn't matter whether you'd collected it early or not, but if that information was gone and you didn't have any information telling you, then you'd get this. Okay, now what's going on here is that we're seeing that there's a rule here about the consistency of your reality. You can't have two pieces of information in your reality that are contradictory. Okay? So once you know that a particle went through there, then you have to get a particle pattern. If you don't know that there was any particles going through there, or that where it particularly went through, then you get a diffraction pattern. Now if you measured the data, let's say we use these detectors, we measure the data. Now it's not a matter of looking at the measured data, it's a matter of are we going to have a discontinuity in our reality or not? You see, so you measure that data. Now if you turn around then and look at this, what are you going to get? So you never look at that data, it doesn't matter. If you look at this, you'll get two spots because you have measured data sitting over here. And then if you erase that data, it makes no difference because once you have a particle in this reality frame, it has to stay here. It has to be a particle. It's not like you can make this thing blink back and forth between these two. You see? All right, this is the way that works. So that's the double slit experiment. So you often hear words like, the conscious intent of making the measurement forces the wave function to collapse. It's conscious intent doing it. Consciousness collapses the wave function. Sometimes you hear that measurement collapses the wave function. It's not really either one of those. It's information being available in this reality collapses the wave function because if you have the information that it was a particle, then it has to be a particle. You can't have the information that it's a particle and then it's a wave. You see, that's a contradiction. So the reality has some rules about being consistent. The reality is informational. Like Fredkin said, your reality is just information and you can't have contradictory information. So that's what's really going on. It's not just the consciousness collapses the wave function. It's not that measurement collapses the wave function. The key ingredient is neither consciousness nor measurement, though both are involved. It's the availability of information. The reality is information-based. Okay, so you have to not violate the rule set or historical consistency. It's the fact of making the measurement and making that data available in the historical record. That's what collapses the wave function. Now I'm going to show you a different picture, one you've probably not seen before. Okay, this is another double slit experiment. And I just show you this. We're not going to go into much detail with it, but one I want to show to you that what I showed you before was kind of a cartoon of the experiment done in the 1920s. This was published in the year 2000. This double slit experiment has probably been has been produced more times, more places by more people than any other single, experiment in the history of the world. So they're still doing these experiments. This one was a particularly elegant and clever experiment because there was a couple of things going on here. Physicists, in an effort to make reality objective, because they needed an objective reality. They wanted an objective reality. That was dear to their hearts. The scientific method is based on an assumption of an objective reality. Right? Scientific method says that you do the experiment and anybody anywhere has to be able to do that same experiment and get that same answer. That's what the scientific method requires. Well, that can only happen in an objective reality. See, so they didn't want to get away from that. They didn't know how. It's not so much really that they didn't want to. It's not that they wouldn't have gone there, but they didn't know how. Okay, reality is a virtual reality. Now what do we do? What do we do with that information? How can we connect that to the world that we know? They couldn't. So that was why they didn't go there. It wasn't really that they had a love affair with Newtonian objective reality. It's just they didn't know what to do otherwise. They were stuck. It was a dead end. And it was a real serious dead end for physicists because here's Einstein. He spent the last 25 to 30 years of his life working on a toe, and that was even a little toe, and he couldn't do it. He couldn't figure out what was that new paradigm that didn't need objective reality. So if your name's Albert Einstein, you see you can work at Princeton for 25 years and never publish a paper because it never works out. You don't find an answer. If you're anybody else and your name's not Albert Einstein, you won't be allowed to stay there for 25, 30 years and not publish a paper. You see, that's not going to work. So if you want a career, you got to work in something that you can get an answer that you can publish. So physics just kind of walked away from this and said, there's no point in going there. If Einstein couldn't do it, if Einstein couldn't do it in 25 or 30 years, can't do that. So what they did instead is they start to deny that this double slit experiment even existed or even was the way it was. It started to just kind of slip away and nobody wanted to go there and talk about it because it was kind of embarrassing that they weren't taking it forward. So anyway, there was a couple of problems. So the physicists who were quantum mechanics theorists, they understood it because that was their specialty. The physicists who were not quantum mechanics theorists, they just kind of said, well, somebody must have made a mistake. They kind of looked the other way and didn't want to do it. One of the things they said is that they said, well, what's going on there? It's not too mysterious. Is that when that photon, let's say, is what we're using to measure which slit it goes through. They say you have to actually touch the particle. Here you have a particle and it's going through a slit. You have to interact with that somehow to make a measurement, right? You can't make a measurement without energetically touching it in some way. And when you touch it, you mess it up. You break that coherence, and that's why you get a particle. That's what collapsed the wave function. It's the act of measuring. Okay. Well, of course, that wasn't true because they let the thing measure, just didn't collect the data, and they got the diffraction pattern. So it obviously wasn't true, but that was conveniently forgotten. So most of the physicists, probably 95% who were not quantum mechanics theorists, had this belief that it was this idea that the energy of the detection is what broke the coherence that gave you the particle. And that was kind of a common fallacy. It is today. If you go talk to physicists today, most of them will tell you that that's what's going on there. Well, here's an experiment that was done and published in the year 2000, published in one of the most prestigious journals. It was Physics Review Letters. Actually, an interesting thing about this is that this experiment was designed in thought, could not actually be performed in 1982. It wasn't until 18 years later that they actually were able to do it. Okay, so it's a hard thing to do. Well, what they did is that here we have our double slit that you can see here. Light comes in, that's all like it was before. But what happens is that when it gets to here, it hits a substance that absorbs that photon, that light that hits it absorbs it, and it spits out two entangled photons. Okay, two photons go out. So that one, it takes the energy from the one and splits off two that are weaker. So energy is conserved. All the conservation laws hold. So now that's the one photon is called the signal. The other one's called the idler. Okay, the names don't mean much. It's just tags that they put on them. Okay, so what we have then is at this point, let's say a photon comes through here, hits this substance, you get a signal, and you get an idler coming down here, two photons that are entangled with each other. When it comes through this slit, you get the signal going up there, you get the idler coming down here. So that right away eliminates the fact that the measurement of what slit it went through, you're not touching it with any energy at all. You're going to determine what slit it went through just by following this idler photon, because it comes down here, bounces off of this prism, gets bent, hits a half-silvered mirror, and 50% of the time, it'll bounce up into a detector here. The other 50% of the time, it goes through this half-silvered mirror, hits a mirror here, goes down to another half-silvered mirror, bounces up to this detector, or goes straight on through to that detector. Now, I know it's all very confusing to follow. But basically what we're saying is that we have 5 detectors all in all. We have this one, number 0, that'll always get a detection. If you go through this slit, it goes up there. If it goes through that slit, we go up there to that detector. And of course, just probability goes through both slits. Some of the probability is going to go up there. So that detector 0 always gets something. But now here, this detector, 1/4 of the time, because we have 1, 2, 3, and 4, we have these 4 detectors. 1/4 of the time, we'll get something in this detector, 1/4 of the time in that, and 1/4 of the time in each of these. The thing that's clever here is, one, he's eliminated the fact that you have to touch that with energy. You don't. Secondly, if we want to know what slit it went through, we get a detection up here. We know it went through that slit. Okay, so whenever that happens, we know it went through that slit. But look, this path here to here to here is much longer than that path, which means that we don't get an identification of what slit it went through until after the screen. This screen is here. That's the same as this screen. Okay, that's the same as this, or that's the same as this. That's where your measurement's being taken. That's already done. So the data's already been collected. And then later, we find out if it goes into 4 or 3, which slit it went through. Or half the time when you go through these half-silvered mirrors, it's a 50-50 chance whether it reflects or whether it transmits. Then it comes into this circuit, and it's equally likely, because of this half-silvered mirror, to either go in this detector or that detector, which means you can't tell which slit it went through, because either slit does the same thing. If it comes down here, it's the same way. It hits this, and it either goes here or here. This one goes up here, and it either goes here or here. So you've erased the information. So in the path that goes to 4 and path that goes to 3, you keep the information. In the other half of the time, when it goes to 1 or 2, you've erased the which slit did it go through information. And in any case, all 4 of these occur after the results already been taken. Okay, very clever experiment. So he covers all bases at once. This is called a delayed choice quantum eraser. That was the name of the paper. So a very elegant experiment. So he's kind of given, this experiment was clever because it met all the objections. It showed there was no way to argue your way out of this one. So the skeptics and the people that tried to ignore it, there was no way to argue your way out of it, because there's no interference, and because your knowledge always comes after the result's already been recorded. Well, what they found, and I'm going to look at, I guess it's the second paragraph in this paper, and it's just a sentence or two. Don't get frightened. I'm reading from a physics journal paper, but I want to read this to you because it shows you some of the politics going on here that I've been describing you. It says, in the 2-slit experiment, the common quote unquote, and this is his quotes, not mine, the common wisdom, imagine eye roll, the common wisdom is that the position momentum uncertainty relation makes it impossible to determine which slit the photon passes through without at the same time disturbing the photon or electron enough to destroy the interference pattern. That's what I was telling you. He says, however, it has been proven that this common interpretation is not true. Well, he didn't mean that he just proved it. It's been proven that wasn't true, for almost 100 years, but this makes it unarguable. Then he produced his results, and I'm going to show you those in a moment. And again, a quote from his paper. Figures 3, 4, and 5 report the experimental results, which are all consistent with prediction. Another eye roll. Same results that we've had since 1925, right? 1924. Nothing's changed, same results. What he was talking about, consistent with prediction, was the Copenhagen statement. Copenhagen statement was basically made by Niels Bohr and Werner Heisenberg, and a handful of other physicists got together and they said, look, we've got this double slit. Here's what it's telling us. And it was just a statement of the facts of what it was telling us. And Physicists didn't really like that Copenhagen statement too much because it was very clear about just exactly what happened. And they wanted to find an interpretation of that result that could be physical, that could be objective. Let's interpret it, we're just interpreting it wrong. Let's interpret it a way that we get an objective reality out of it. So then they started calling the Copenhagen statement a Copenhagen interpretation. Now that was just one interpretation. There are probably 25 or 30 interpretations. If you go look up this on the internet, you'll find all sorts of interpretations, all of which are trying very hard to make this experiment go away and become a supporter of objective reality, and none of which of them work. Matter of fact, it's interesting that Einstein was one of the ones who had a real hard time believing this. He made a couple of comments about how he didn't think, God played dice with reality or something. He uses God as a metaphor. He was not a religious man, but he had a hard time with that. Matter of fact, a little interesting side note, he and Podesky and Rosen, it's called the EPR, Einstein, Podesky, and Rosen, they were going to crash quantum mechanics. They were going to show why it was silly and it didn't make sense. So they took the Copenhagen statement and they said, well, look, if this is true, then here's the logical consequences. Something ridiculous happens that obviously will not happen. You can have these entangled pairs on the opposite sides of the universe, and if one of them changes, the other one would instantly change. It's called entangled pairs. They predicted that that would happen, and that was obviously ridiculous. You couldn't have two things that if you flip one, you'd flip the other immediately, because information can't travel that fast, et cetera, et cetera. And that was posited as a proof that quantum mechanics had a flaw in it, and it just wasn't right. Well, some 20, 30 years later, they finally were able to do the experiment, and guess what? Entangled pairs, yes, it's like that. You flip one and the other flips immediately on the other side of the universe, and oops, so Einstein, Podesky, and Rosen kind of went down in flames on that. In quantum mechanics, the Copenhagen statement was the winner in that contest. So that's just kind of an interesting historical thing. Einstein had a hard time with letting go of objective reality. Okay, now here's the result. And just as you would expect, every time that the information of which slit it came through was erased after the fact of collecting the data, they got a diffraction pattern. So here it is when it went into detector 1, and here it is when it went into detector 2, because 1 and 2 were both when it got erased. Okay, now remember that when we have these two things, every time a particle comes in, you get a dot of light someplace. So even when you're doing this one, you send a particle in and blip, you'll get a dot of light up there. You send another one in, you may get one down here. You send another one in, it may go there. It's that sort of thing. And it was the same with this experiment I just showed you. You send the dot of light in, you've got 4 detectors for the idlers, and you'll get a dot of light in one of those 4. And you'll always get a dot of light in number 0, which is where the screen was. And then where you do know what slit it came through and you have that information in this reality frame, and guess what? You got a pile up in right behind the slit. And you got another one that looked just like that for the other slit. They were just tiny bit removed because the slit's just tiny bit separated, so he just showed just one picture. So it worked exactly the same. All right, I'm going to do this one slide and then we're going to take a break. It's important to go over this because if you understand this experiment, you basically understand more easily how consciousness works. Fundamentally, what it tells us is that reality is not objective, period. The one thing I wanted to go through is I wanted to tell you now we're back to this picture, and I just wanted to do this in a way that makes it easier to understand. I just explained that other experiment, but it was complicated, I know, it was hard to follow. So let me put it back into the form of this so that it makes it easier for you. And it's going to sound different because I'm going to give you a logical equivalent of that experiment that we just looked at. Okay, consider 2 physicists, A and B. Okay, they do this experiment here at the bottom. They have detectors, they detect what it goes through, and they keep the track of the results. So they're doing this experiment with the detectors, and they're going to do that, let's say, 102 times. Okay, so now we've got just one after the other after 102 times. Now, they take the results. They don't look at any of the results. They just take the data. Okay, and the way they're going to take that data is that they'll run it once. They'll take the data from the detectors, put it in an envelope, says experiment 1 detectors. Take the data from the screen over here, say experiment 1 results. And put that in a little envelope. And they'll take those 2 envelopes and they'll put it in a bigger envelope that says experiment 1. All right? So now they're going to do this 102 times. Now they look, when they're done, they take all of these envelopes and they have them here and they look at the first one and they open it up and they look at the result here and sure enough, that's exactly what they got. And then they look at the last one, just to make sure nothing happened and the experiment was running all the time. They look at the last one, number 102, and they open it up. Sure enough, this is what they get. So it should have not changed anything in between. Then they take all the envelopes, they put them in a safe. They lock them up in a safe, and they're the only 2 that have the combination. They come back a year later, they're going to have a big press report, and what they're going to do is they're going to open up the safe. They take these envelopes. Now they've got 100 of them left, right? They used the 2 out of the 102. They're going to take these envelopes, and they're going to randomize them. Just mix them all up, randomize them, shuffle them into 2 piles. They have 2 piles of 50. Now, 1 pile of 50, they're going to look at the data. They're going to pull it out. They're going to look at the screen. And when they look at that screen, what are they going to see? Well, they're going to see this, right? That's the experiment they did. So they do that for the first 50. They pull it out, they look at that screen, and there they are, just like they're supposed to be, all 50 of them. Now the other 50, they take out all the envelopes that have the detection data in it, they set them on fire. They burn them. Oops, detection data's gone. Doesn't exist in this reality anymore. And then they take a look at the result, and guess what? The other 50 all have that pattern on them. They all have diffraction patterns. You see? Now that's a logical equivalent of what I just showed you in that delayed eraser experiment. That's what happened, you see. And there was no way to argue with it because the quantum itself made the choice of what experiment, of what detector it went to. There was no hands touching it. There was no energy touching the detection. It just removed all the points of argument that anybody had ever looked at, and eyes rolling. It came out exactly the way it had come out, in every experiment for the last 87 years. Okay, so that's the idea. Now let's give it a little bit of a twist to it. Okay, let's say that B, it was two physicists, A and B, did this. Let's say B, on the night before the big press conference where they're going to pull these things out a year later, B sneaks in and he pulls the envelopes out of the safe, sets up a movie camera, looks at all the data, shows it to the camera, returns it to the safe so you couldn't tell that anybody had ever opened it or looked at them. And then the next day comes and A comes in and he takes them all out and he does just what we said. He sorts them, he burns one half and whatever. And what happens? All 100 look just like that. Why? It's the data. You can't have a conflict in data. We already have the data of what they look like. And when you look at all the data, all 100 of them are going to look just like that. So that's what happens. Okay? What happens is that you get a big sigh of relief from all the physicists attending and say, I told you so. The thing doesn't work. Now let's say that B, after he makes the movie, returns all the originals to the safe, being happy with what he's done, he takes a little nap, and while he's napping, the building catches on fire. B burns up in the fire, so does the camera, it's all destroyed. Now what happens? Well, we're back to the scenario 1, right? The same thing happens that happened the very first scenario. When they shuffle the envelopes and they burn the data of all the ones where the detection data was burned, you get diffraction patterns again. It didn't matter that A had done that because it came into this reality and then it left. So it's gone. There's no inconsistency now. You see, there's no inconsistency. We don't have data saying one thing and then other data saying the opposite thing. As long as it's consistent, that's what we have. Well, now let's say that B does that. He goes in and he opens the safe, but instead of making a movie, he just takes individual snapshots. He opens every envelope and he takes snapshots of the data. And then he has all these snapshots, but they're unlabeled. He just took the snapshots, they're unlabeled. And he walks out of the building, gets run over by a truck, and his snapshots get spread all over the ground. Well, what's going to happen? Well, there's the data. It's sort of here, but it's unlabeled. Since they all look exactly like this, it almost looks like he just has 100 copies of a single photograph. What happens? Well, same as the initial one, right? The 50 that get burned, where the detection data gets burned, come out like this because there's no proof. There's no evidence that it was any other way, okay? Okay, let's do it the other way. He does make the movie, and he walks out, and he gets hit by the truck, and there's the movie camera. Dented, but still works. The data's still in it. Nobody knows necessarily he's been in there or what's on the film. It might be possible that somebody would take it and say, oh, look, found a dented camera on the street. Let's delete what's on it, and I'll take pictures of my children. Okay, but that doesn't happen. But it's just laying there on the ground, or gets picked up and put with the effects of whatever was left of him after he got hit by the truck. So the data is still there in the camera. What happens? Well, all 100 turn out to be like that because now there's something in the reality that would conflict with anything else, you see? So it's the consistency of the reality. The reality has to stay consistent as long as that's data there. Now, if somebody had picked up the camera and deleted it off the camera, then we would have gotten these, wouldn't we? You see how strange this is? And all this happened a year later, you see? This can't happen in an objective reality. This is impossible. This is a logical equivalent to what I just showed you in that delayed erasure experiment. Here my delay was a year. In their delay it was a few tenths of a second or something, a few milliseconds behind. But it doesn't matter. If it's past, it's past. Whether it's a year or a decade makes no difference. So physicists who have spent the last 87 years in denial, making up interpretations of this experiment that still leave them an out, with reality being objective. You see, that's why when these guys published this experiment, they said about the common wisdom, with the eyes rolling and listen, what were the results? Well, the results were that it verified everything that we already knew. It wasn't like this was, wow, it's like it's always been this way. Now, we're going to do a little comparison of quantum mechanics then to quantum mechanics now, and you'll get a bigger picture of what's really going on here in the science world. I have some quotes. Werner Heisenberg was one of the inventors, one of the co-inventors of quantum mechanics. Mostly quantum mechanics took place on German soil until it was published and others got involved in it. Werner said, the only thing that can accurately describe an elementary particle is a probability function that in itself contains nothing about the quality of being or the physical existence of that particle. Okay. Niels Bohr. Werner Heisenberg and Niels Bohr were actually the two main players in putting together the Copenhagen statement. Niels Bohr said, the common sense view of the world in terms of objects that really exist out there, independently of our observations, totally collapses in the face of the quantum factor. Now the quantum factor, he just meant quantum mechanics. This one I like a lot from Niels Bohr. If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. And now we're starting to get some that, here's one that kind of points the direction of a solution. It says, every great and deep difficulty bears in itself its own solution. It forces us to change our thinking in order to find it. What he's saying there is that we need a new paradigm. The old paradigm, Newton's paradigm, isn't right. We need a new paradigm. Of course, Bohr and Heisenberg are both Nobel Prize winners. All the people I quote here are all going to be Nobel Prize winners, all top physicists. Now, Albert Einstein, remember we quoted before, he says, hence it's clear that the space of physics is not in the last analysis anything given in nature or independent of human thought. Right? That was from Einstein. Another one from Einstein, reality is merely an illusion, although a very persistent one. And these I did Friday. I did these yesterday. So those of you who weren't there yesterday, I'll repeat them because they're very interesting. Wigner says, it'll remain remarkable in whatever way our future concepts may develop that the very study of the external world led to the scientific conclusion that the content of the consciousness is the ultimate universal reality. So these now are the top physicists, Nobel Prize winners back in the 1920s and 30s. Saying things like this. Max Planck, another one of the brilliant people that were at the very beginning of these sciences. He said, science cannot solve the ultimate mystery of nature because in the last analysis, we ourselves are part of the mystery we're trying to solve. Which means, what's out there, this outside world that we thought was objective is somehow entangled with us. We're part of the thing we're trying to understand. The solution. Einstein said, no problem can be solved from the same level of thinking that created it. What that means is that if you can't find a solution, you probably need a new paradigm. You probably need to change your beliefs about the nature of reality. And of course, that mirrors the one that the last bullet up here from Bohr about every great and deep difficulty bears in itself its own solution because it forces you to new thinking, forces you to a new paradigm. Okay. They knew that objective causality was inadequate, and they knew that a whole new paradigm was needed. And here I'm going to quote a letter from Einstein, who worked on this new paradigm called unified field theory. 25 to 30 of his last years, he worked on this. Now, he was only actually working on a little toe, and that was to make quantum mechanics and relativity both derivable from something at a higher level, some overarching understanding that you could get both of those, because he saw that each one of those denied the foundation that the other was based on, and he said that means there must be something else, something at a higher level that can describe them both. So after almost 30 years of work, Einstein wrote a letter to Bohm, who was another physicist, very well thought of physicist who worked with Einstein on this. He said, one has to find a possibility to avoid the continuum. In other words, reality wasn't continuous, it was discrete. It's digital. Time, space were digital. Together with space and time altogether, but I have not the slightest idea what kind of elementary concepts could be used in such a theory. See, hit the wall, couldn't come up with that paradigm. They all knew that a new paradigm was necessary, but couldn't find, the time for finding that just hadn't happened yet. All right, now we'll contrast that with quantum mechanics now. Okay, I have some quotes, and I'm quoting Richard Feynman here. Richard Feynman was a great physicist. He's dead now. He's been dead for a decade or so. But he was a quantum mechanics theorist. He knew what quantum mechanics said. He knew what the double-slit experiment meant. And he actually probably knew more than the founding fathers of quantum mechanics, because quantum mechanics had learned a whole lot in those years between Feynman and Bohr and Heisenberg. But what they learned mostly was better ways to calculate, better ways to crunch, better ways to come up with answers that were verified by theory. So here's some quotes from Richard Feynman. The first one is obviously true. The double-slit experiment contains the basic mystery of quantum mechanics. True statement. The second one was, shut up and calculate. Now, why did he say that? That was his response to the graduate students who asked him, Dr. Feynman, what's going on here? Why is this like this? What does this mean? He said, shut up and calculate. He also said, I don't understand quantum mechanics. And quantum mechanics represents a phenomena that is impossible to explain in any classical way. Well, what did he mean by classical way? Yeah, objective causality. It's impossible to explain in any acceptable way, which is objective causality. Here's a quote from David Harrison, Dr. Harrison, Department of Physics, University of Toronto, and I just pulled that up off the internet because I was coming to Canada, and it's just to show you that any physics department anywhere in the world, you will get these same quotes. It's not that, you know, these fellows are kind of not getting it. It's just that this is the way physics is out there today. These are representations, Feynman particularly, world-renowned, very top-notch, and I'm sure Dr. Harrison is as well. Dr. Harrison said, "It may be true that nobody can understand quantum mechanics in the usual meaning of the word understand." Well, that usual means in terms of objective causality, right? So what are we finding? We saw in the quantum mechanics then, we were finding these scientists, they were excited, they were thrilled, they had this big breakthrough right in front of them. We need a new paradigm. Then we have Einstein working for almost 30 years, fails to produce one. And now today it's like, it's impossible. Nobody can do it. You see how we've changed our viewpoint of this? Now it's impossible. Shut up and calculate. Don't go there. It's impossible. Okay, well, when you believe that something's impossible, what's the probability that you're going to solve that problem? 0, because you stop thinking about it. Why should you start worrying about the impossible? It's impossible, it's possible. You know, accept it and go on is kind of what we have. It reminds me a lot about some of the fundamentalists. You know, you have some of these folks that claim that the universe can't be more than, 7,000 years old or something, because that's what somehow they get that out of the reading of the Bible. And when people point out to them, but these dinosaurs are like, 6 million years old, and it takes a sun like, 1 billion years or 50 million years in order to, coalesce and get to the point that it really is a sun, So the universe has to be much, much older. And they go, nope, it's not like that. Why not? Oh, it's a conspiracy. So all those scientists, you see, are ganging up to try to make us fundamentalists, look wrong. So it's just, they make all that up. Those dinosaur bones were all planted there, It's all a trick. So again, a conspiracy theory will explain anything. So that's what you get, and I can just see, some young kid goes into that fundamentalist minister and says, but hey, I've just been reading this book, and it says that the universe is 5 billion years old, and then the minister turns to him and says, just shut up and pray. Right? That's the same as shut up and calculate. It's the same thing. This is scientific fundamentalism that we're talking about here. It's a scientific belief. So they're stuck. What's the big problem? Well, the big problem is that they believe it's impossible, so they come up with justifications. Just like the conspiracy theory that, must be the scientists trying to do in religion. They come up with ideas that try to justify their position. Now, Feynman, he knew quantum mechanics as well as anybody's ever known quantum mechanics. Brilliant guy, quantum theorist. He just couldn't bring himself to say in public that reality was not objective. That was not acceptable. Yeah. Instead, he said, shut up and calculate, and I don't understand quantum mechanics, and it's impossible to understand in quantum mechanics. Of course, that got him off the hook. If it's impossible, that was a good reason why he didn't understand it. It was impossible. Okay. The reason is that the whole premise upon which science is based, the scientific method, is threatened. Okay, the scientific method is based upon the assumption of objective reality, and a probabilistic statistical reality is not objective. It fluctuates, it changes, it randomly draws a result from a distribution of the possibilities. How can we live like that? not good. Scientific method is the most precious and productive intellectual jewel in Western civilization. Scientific method delivered us from the dark ages, if you will, of thinking. It cut through all of the superstition. It made science into real science, right? All the stuff that we have here, all this technology, all came up through discoveries made based on the scientific method. So physicists have a hard time giving up that objective reality. Here we are in the information age based on largely the application of this scientific method. And it's wrong. Everything the scientists believe for the last 200 years goes up in smoke. No, not true. It's not true that it goes up in smoke. Scientists fail to appreciate the history of paradigm changes in the nature of reality. See what happens. If we look at probably one of the first major paradigms was flat Earth. One day turned into a sphere, right? There was a big paradigm jump. Well, what happened to the flat Earth? Did we just discard it? Say, it's not flat, nobody, don't. No, we still use a flat Earth as an assumption. All the surveying that's done anywhere, it's done on a basis of a flat Earth. When they go to survey, they survey on a flat plane. Why? Because it would be silly to take in the Earth's curvature when you're only surveying, 10 acres, in a field someplace. The amount of difference that you'd get in curvature, to change the square footage would be in your 10th decimal place, and there's no point in going there. So the flat Earth becomes a very good approximation over short distances, and we still use it. Okay, so you don't throw things out. They just become a subset of a larger picture, and they still hold true within that, within the range of which they're valid, which for the flat Earth is short distances. Now, what about Newtonian physics was replaced by quantum mechanics and relativity? Okay, but do we throw out Newtonian physics? Nobody does F equals ma anymore? Of course not. We say, well, quantum mechanics and relativity now are a bigger picture, but Newtonian physics is an approximation in the space where things don't move so fast and they're not so small. And guess what? Probably 95% of all the physics that's done outside of academia is Newtonian physics, because things aren't moving that fast and they're not that small, and Newtonian physics works. And to try to do quantum mechanics, say there, instead of classical mechanics, which is Newtonian mechanics, would create a lot more computation, and it would only give you a difference in, again, the 15th decimal place. So there's no point in doing that. So what happens is that when you have a shift in the reality paradigm, the old paradigm just becomes an approximation inside of a bigger picture. So it doesn't mean that when we go to a virtual reality, suddenly physicists are all unemployed because there's no objective reality for them to work on anymore. It just means they're working inside a subset. Their objective reality becomes a subset, an approximation to the larger reality. Okay, well, what is this subset? It's the subset where uncertainty is small. Okay, it's where uncertainty is small. That's the subset they'll be in. Whereas Newtonian physics was in not so fast and not too small in size and speed was the subset. But now it's uncertainty is the key thing. You see, in uncertainty and information kind of go together. So we're going to work all this into the idea that reality is information. So now why did these things turn up, let's say in quantum mechanics? Why did it turn up in the double slit experiment with little particles? And why do physicists today maintain that quantum mechanics only applies to little things? Well, it turned up in quantum mechanics because there's a lot of uncertainty in a little particle like a photon or an electron. When we try to determine its position, just exactly where is that electron? Now we're dealing with just one electron. Just where is that electron? Well, we don't know exactly. You see, there's lots of uncertainty with its position. There's enough uncertainty with its position that its probability function spreads out across both slits and can go through both slits at the same time. You see, so It's because there's lots of uncertainty there with little tiny things that we can't see, is why we have the double slit experiment is the place where this shows up. But quantum mechanics, the same principles apply everywhere. Same principles apply to our everyday life. We just don't see how. We just don't understand it, but they do, and I'll explain those in just a little bit. So relativity and quantum mechanics are on the cusp of becoming a subset of a larger, greater truth, subsets of a big toe. Okay? A more complete and holistic science, though most physicists are not aware of this fact because it's still very early in the struggle for acceptance. However, it will become accepted because it answers the big questions in both physics and metaphysics. You will soon find out why future particles are probability distributions. That's particles that haven't been measured yet. And why C is a constant? I just was told that there's some research going on today as we speak that perhaps they found a neutrino that goes faster than C, but we'll see how that works out. You know, that would be real interesting. It'd be nice if that was true, because then it would give us actually some new data rather than just same old, same old. You know, it'd be kind of interesting because then it gives us new possibilities. But we'll see how that works out. We'll see how that gets integrated in. Every time you get new information, it's an opportunity to expand your theory, to make it more general. So that's good. We'll find out things like way Paralabs. Paralabs, PAIR is an acronym. It stands for Princeton Engineering Anomalies Research. Paralabs is an organization that's been, for the last probably 25, 30 years, they've been looking at mind, matter, interconnects, immaculate scientific protocols. You know, they're basically out of the physics department and engineering departments of Princeton, which are pretty strong departments. And their protocols are immaculate because they knew nobody would believe a word of what they were reporting unless their protocols were immaculate. And you'll see that we're going to explain how all that stuff works. We're going to explain things like synchronicity and how the placebo effect works and how you can heal with your mind and what your purpose is. All that kind of falls out of this idea. So we see the big difference between the physicists then and the physicists today, that the physicists today have given up on finding that new paradigm, which is basically the paradigm I'm going to be bringing to you today. Okay, we live in a statistical reality. Let's just start there. Objectivity is only an approximation, and that's true for several reasons. One is that there's measurement error. You can never measure anything exactly, right? You can never measure anything exactly. So if we look at something like the sun, okay, let's measure the sun. How heavy is it? What's its mass? What's its pressure? What's its temperature? We measure all those things. Well, how do we do that? Well, we measure it statistically. Its mass is no bigger than this, no less than that. Its pressure is within these bounds, right? Its temperature goes up and down. Why? Because it's fluctuating all the time. It's not exactly always the same diameter. It's got a lumpy shape on it. You know, it's not always the same temperature. You got things going on. It's changing all the time. So you can only describe it statistically because it's changing. All right, now let's do something that's a little less changeable, something that's really fundamental, maybe as solid as a brick. Okay, now let's go measure a brick. How long is the brick? Well, to the first 2 decimal places, probably most scientists would agree. The further you get down on decimal places, the more disagreements you'll get. And if you gave 100 different teams of physicists the idea to measure this same brick, you'd get 100 different answers. Say the first few decimal places would be the same, but different answers. Why? Because a brick isn't quite as still as you think. It's not as volatile as the sun, but you look at a surface of a brick, it's not smooth. It's bumpy, it's lumpy. It's got all kinds of dips and crevices and peaks and mountains and gouges in it. It looks more like the surface of the earth if you get down close enough to it. So where does it start and where does it stop? Where do you start your measure? On top of this kind of peak of the edge or at the valley, or do you do a statistical mean of where they are? And then let's get down even smaller. It's on molecules. Those molecules aren't standing still. those molecules are vibrating, they're moving, they're jumping all around. So how do you measure exactly how long a brick is? You can't. All you can say is, well, it's, no bigger than this, no shorter than that, statistically. So everything's really statistical. There is nothing that is objective. You can't measure something that's objective. You don't here's a brick, it weighs 3 pounds and it's exactly 12 inches long. That's an approximation. So even that alone kind of negates an objective reality. But besides that you have the human error of the people doing the measurement, you have the measurement equipment error, right? And then you have that the thing itself is always moving around and undefinable. Exactly. So you've got all those errors. Besides that, though, at a more fundamental level than just measurement error, a future sun, like everything else, a future brick, a future atom, a future photon, a future statistical analysis or dead tree line on the ground, they exist only in probability and are brought into this reality frame by measurement. You make the measurement, and then you have the data available. The result of a particular measurement is randomly sampled from an array of discrete possible states that represent the probable future at that instant. However, once the measurement's made, the result must fall within the natural uncertainty of the data that goes with that object or process. In other words, you can't have a brick. We say it's from plus or minus. Maybe bricks are made in the brickyard plus or minus 1/100th of an inch, maybe, if their equipment is good. You'll never get a brick come out of that equipment that's 2 feet long instead of 1 foot long, because that exceeds the natural uncertainty of the process. But you have fluctuations within that. So within that uncertainty, there may be 100 different sizes that brick could be within the confines of the natural uncertainty of the equipment. And all of those are probable. And you reach up into that distribution and you pull out one, and that's the way that brick is. You see, you make a measurement. Once you make that measurement, you get that result. So quantum mechanics is based upon probability. It's not true just for the very small. It's true for bricks as well. The macro world works like the micro world. Like I said yesterday, I was always very skeptical, if you will, of a science that only applied to little things. Quantum mechanics, they'll tell you, only applies to little things, but that just never computed well for me. Science, if you have general principles that apply to the world, the idea, well, they only apply for little things. They don't apply for everything. That means that before one determines whether or not this rule will apply to you or not, you have to define, are you little enough? Is this particle little enough that we can apply this rule, or is it just too big that maybe we can't apply this rule? It's like it shouldn't be like that. You have a rule, and a rule works. If your rule only applies to little things, then you don't have the right rule. There's something more fundamental than that rule. What you have is an approximation, and an approximation will only apply, the approximation gets worse as you get bigger. So it's that sort of a thing. So the objective world is another one of those scientific beliefs. Every object and every interaction contains some uncertainty. Before we get out of physics, we're almost out of physics here. We've got just 2 more slides, and then we're going to get into metaphysics for a bit. We'll see that the future probability distribution, we haven't talked about that yet. We're going to talk about that when we get to virtual realities. But we're going to see that the future probability database is where those future particles reside. That's why you have a particle that is a probability distribution, because it hasn't come into this reality frame yet. And everything that's in the future that hasn't come into this reality frame yet is probability, including the state of your health and the size of that brick and everything else. Okay, this is just a little cartoon that will show you why light travels at the speed c and why it has to be constant, or why there is basically a constant information transfer in our reality. Now, whether that turns out to be a little bigger than we thought it was because of this new experiment or not, it's not the point. The point is that you'll end up with a constant maximum speed. Okay, these green blocks represent chunks of our reality, chunks of volume. Okay, don't tell anyone that I told you that our reality is little green boxes. It's just a cartoon. So here's a delta V. Okay, here's a delta V. These are just 4 little chunks of space. Okay, now, if you're making a virtual reality, what is it that you need to know? What are the things you're going to go out and you're going to build a competitor to World of Warcraft? What do you really need to know? You need to know, how big a computer am I going to have to buy to support this thing? You know, that's the main thing you're going to know. What infrastructure do I need to be able to run this game? And the way you do that is you say, first, I need to know what's my pixel count? How dense is my information going to be? How much fidelity am I going to have with my pictures? Because every pixel that you have to illuminate is data that you have to store. Okay, so that's the one thing. What's the pixel count? Well, in the 3D world, in our virtual reality, pixel count comes not in area, but comes in volume. Our pixels of 3D space are little chunks of volume, and that's what those green boxes are. The second thing you have to know is, how often do I have to update each of those pixels? In other words, the refresh rate. You know, how many times a second do I have to change the color and the intensity of that pixel? Okay, that tells you now your computer's throughput. How fast does that computer have to work? If you have very high pixel density, then you have lots of data. If you have a very high refresh rate, you have to move that data very fast. So those are the 2 central things you need to know if you're going to build a virtual reality. And we're going to see that the speed of light specs those quantities for us in this virtual reality. Okay, so the frame rate is now our update rate, right? It's our refresh rates. The frame rate for the simulation. Remember, simulations work by progressing a delta t at a time. You have a simulation, t is equal to t, and then you calculate everything, and then you go back through that time loop, and now t is equal to t plus delta t. You increase your time, 1 little delta t, you go through and calculate everything again, and then you increase your time, 1 more delta t, go back and calculate. You keep doing that. That's how a simulation runs forward in time, 1 delta t at a time. Well, that's our refresh rate in this virtual reality we have. Okay, so what we have here. Let's talk now about information in this reality. So here's a cell. If you have information and you want to move that information from one place to another, the fastest way you can do it in a well-behaved reality, and by well-behaved I mean it's homogeneous, isotropic, and linear, okay? Unperturbed space has to be that way. The fastest you can move it is from one cell to the next cell to the next cell to the next cell. If you skip cells, if you say, oh, I'm just going to go every 4th one, I'm going to go from here and I'm going to jump over there, I'm going to skip 2. That's called teleporting. Things jump around in that reality. They're not consistent. They don't appear to be continuous. They're really not continuous anyway, because every delta t, the time goes up, right? They're just jumping a little bit of delta t, but they can only move one cell at a time so that you don't have things flying around. Okay, now, what about those cells? They have to be constant. They have to be the same size. They have to be a constant size. If not, I'd put my ruler over here in space, and these would have big volume cells, and the ruler would be this big, and I'd put my ruler over here, and they'd be little tiny volume chunks, and now my ruler would only be this size. You see, you can't have that going on in your reality either. So you don't want a funhouse reality where things are distorted, and that doesn't make a good learning lab. A good learning lab, a good place to learn, to grow up, has to have consistency. It has to have feedback that you can depend on. You don't want a funhouse reality. So that means that there's two things here that need to be a constant. The delta V here has to be the 3D pixel, this delta V, and the frame rate, this delta T, both have to be constant. If delta T wasn't a constant, you'd be in this constantly speed up or slow down. You know, time would be jerky. Another funhouse reality. Well, if you take delta V and take the cube root of a volume, you get a distance. Divide that distance by the frame rate, you get a velocity. And that velocity is what we call the speed of light, and that says that's as fast as information can go from cell to cell to cell to cell. So that's the upper limit then on the speed of the transfer of information. And it has to be a constant, otherwise we would not have a homogeneous isotropic linear space, and we would live in a funhouse. We would not have a consistent experience here. Things would pop around. You'd come to class and suddenly, there would be no books there, or no chairs, or no desks, because that would have all teleported away someplace. You'd have that kind of squirrely reality. That doesn't work. It's not a good reality. So basically, that's why C is a constant, because delta V has to be a constant, because delta T has to be a constant. Okay, so pixel size and frame rate determine how much memory and how much throughput is required in our virtual reality. Okay, they specify the size and speed of the resources needed to create this virtual reality that we live in. Our physics and our rule set depends on X and T being homogeneous and isotropic. Our rule set requires delta V and delta T to be very small constants. Delta T is called a Planck time. It's about 10 to the minus 44 seconds. And delta V, or the X, you take a cube root of that, it's called a Planck length. It's about 10 to the minus, I think, like 35 or something meters. Okay, so that's why C has to be a constant, because we live in a virtual reality that is not a funhouse reality. All right, so relativity theory is the logical consequence of C being constant. No, that's just a fact. That's how Einstein created relativity. He started with that assumption. The rest of it's algebra. C being constant is consequence of reality being digital and virtual. The magnitude of C represents a constant that specifies the demands placed on the virtual reality rendering engine. Okay, and C is specified, but when I say specified, I mean evolved, right? It evolved to suit the available computational resources within the larger consciousness system and the fidelity requirements of the reality. Well, let me mention a little bit then about reality, or this virtual reality, and where it comes from. I may be jumping a little ahead, but I think it's a good time to do it. So where did this virtual reality come from? Why do we have it? Why is it, how did it get here? World of Warcraft was programmed. Programmers went in, and every tree that's in World of Warcraft had to be put there by a programmer. Every blade of grass, if they got that much detail with blades of grass, would have to be programmed. They don't. They have just kind of a green carpet effect, because that's too hard to do all those blades of grass. It had to be programmed. Okay, what about this reality? You say, wow, that'd really be big programming, right? I mean, this is a big whole universe. You have to program every tiny thing in it. Well, of course not. It wasn't programmed. It evolved. What did it evolve from? It evolved from the big digital bang. What's the big digital bang? It's a simulation. It created this virtual reality. That's when the control room pushed the run button, and they had in their computer specified a bunch of energy under certain pressure and temperature, and then those were all their input constants, right? That's how they defined it. They had the rule set, things like gravity and physics and stuff. They had this rule set, and they punched the run button, and inside that computer, that suddenly it was released, and those gases expanded, and eventually they coalesced into stars, and then some of them turned into, had planets, and the planets sometimes circle around stars, and they had oceans and molecules that came together, amino acids, and ended up with cells, and then the cells split, and then the cells turned into people. You see, you have biological evolution. Here we are, all in a simulation, just a simulation. That's where our virtual reality came from. Okay, and that simulation now has tremendous amount of detail, because it had this rule set that was all of science. All we know of science and all the science we don't know is basically the rule set. And out of those rules, and actually there's not that many. If you boil science up, you can get just a couple rules that say an awful lot. Like all electromagnetics into like 4 equations that Maxwell wrote, even though electromagnetics is a huge subject with lots and lots of detail, and it all comes down to a couple simple things. So there's just a couple simple things, and here we are. So that's the big difference between us as a virtual reality and World of Warcraft or The Sims as a virtual reality. We're an evolved virtual reality, and we're still evolving, right? It's not that that simulation's over. It's a slow process, so we don't notice it. We think it's always been this way and it always will be this way, but everything is still evolving. Okay, now let's drop the science for a bit. We'll get more into consciousness. This diagram, they look like maybe little brains up there, but they're not brains. There's just a little cloud of consciousness. Consciousness 1 and consciousness 2. Now, what I want to depict with this is give you an idea of how consciousness has to communicate and what the logical implications are of that. So consciousness is just part of an information field, right? And consciousness can only send and receive data. Okay, so here's two consciousness, 1 and 2, and consciousness 1 wants to send some data over to consciousness 2. And you see the data that it wants to send is this pointy little star. That's its data. It's got that metaphor, and it wants to send that little pointy star, this little pointy star. It wants to send it over here. Now, how did it come up with that little pointy star? Well, that little star is a metaphor. That star is a symbol. It's a metaphor. So it came up with it out of its own experience is how it had to come up with it, right? So that's experience 1. You know, I1, the information 1 is a function of experience 1. So out of its experience, it says, oh, here's a symbol, here's a metaphor from my experience, and sends that data over, and consciousness 2, you see, didn't get it quite right. Consciousness 2, how do they receive that data? Well, they just get the data, but they have to interpret it. How do they interpret it? They have to interpret it from their own experience. Now, it's very unlikely that these two consciousnesses have exactly the same experience. No two things have exactly the same experience. So this one who created that from its experience, and this one who interpreted that from its experience, you see we have a communication problem here, don't we? Communications are not too exact. You get data defining this reality, and then you have to interpret that data. And the way you interpret it is personal. It has to do with you, your experience base. So we have this fundamental problem with trading metaphors and trading symbols, and nobody can ever really communicate exactly what's going on. We're still digging down into that. There is no objective reality. Okay, all reality is personal. Okay, you make your own reality and integrate that personal reality with a common environment, shared interactive data, which must be interpreted. And it's interpreted based upon you, which means based upon your knowledge, your belief, your fear, your expectations, your understanding, and the feedback you've received. All of that goes into it. We all have experiences, but experience is subjective. You can never share an experience with anyone. An experience is just yours. You can share metaphors, you can share an explanation and description, which is based upon your own fears, your own beliefs, your own knowledge, and whoever you're trying to share it with will interpret it. What you've told them, they'll take your metaphors and your symbols, and they'll interpret that in terms of their own beliefs and their own fears and their own metaphors. So you cannot directly share an experience. This is just the nature of consciousness. Okay? It's not objective. It's entirely subjective. So the appearance of objectivity, when we share and we say, yeah, all of us, we see the same thing. There's a blackboard up here and we're kind of sharing this sort of thing of our experience. The reason that makes it appear objective is just the commonality of viewpoint. We all have roughly the same sensors. We all see, hear, and feel all in kind of the same small band of energy. So we all kind of get mostly similar things. And because we all grew up in mostly similar cultures, we all sort of interpret them more or less the same way. Talk to somebody who's in a drastically different culture. You know, say somebody out of the Amazon jungle, and you'd find out that communication was really, really difficult because you didn't share a cultural background with common metaphors, you see. So this is just the nature of consciousness. Okay, so now let's talk a little more about consciousness and where it is and where it comes from. Consciousness is the fundamental reality. Consciousness is a digital information field. Okay, at the most fundamental level, consciousness is just data. It's just information. At the most fundamental level, information is just bits. And at the most fundamental level, bits are just binary. So if we're working this down to the simpler and simpler levels, we end up with bits that are binary. What's that? That's a 1 and a 0, an on and an off, a hot and a cold, just two states. That's it. So at the root of consciousness is binary. The simplest root. That doesn't mean you couldn't do something else. You could have something other than binary, but it wouldn't be quite as simple. It would have its own complications. Information is non-physical and subjective. Thus, consciousness is non-physical and subjective. Information is non-physical because information is the meaning, the content, the message, not the media, not the code symbols. So this piece of paper I'm looking at, this paper, it's the media, right, is the paper. The ink on here, that's the code symbols. Those are both physical. They both take up space, they both have, they have volume, they have mass, they have all the properties of something that's physical in this reality, but they're not the information. It takes a consciousness to get the information. It takes a consciousness to get the meaning, the content, and the message. No consciousness, no message, no information. Take a camera, take a picture of this piece of paper, and the camera didn't get the message. It got a picture of the paper and a picture of the code symbols. So the paper and the code symbols, the media and the code symbols allow you to store and transfer information, but they're not the information. Information is non-physical. The meaning, the content, and the message has no volume, has no mass. It's not physical. Okay? Next slide here, we're going to talk about evolution. Evolution and information systems. Okay, we see that information in a digital system is represented by organized bits. And information systems have entropy. Okay, so let me talk a little bit about the word entropy. Information systems have entropy. Now, if you were in the information sciences, entropy would be a very familiar term with you. If you're a physicist and do thermodynamics, entropy would be a very familiar term. A lot of people, entropy is not a very familiar term. It's a difficult term to get your arms around. But all entropy is a measure of disorder. Okay, so if we let's take a bunch of Tinker Toys. Okay, and we just throw them on the floor, dump them out of the box and let them roll around the floor. They are basically randomly associated with each other. There's no association, it's just random. Randomness represents noise when it comes to information. In information, you talk about signal, which is information, and noise, which is basically random energy. Signal is energy with a lower entropy. Okay, so those Tinker Toys that are all spread around have no relationship to each other, but now you take two of them and you stick them together. Now those two have a relationship. And you take another one and stick to that. As you build structure, you end up with content, meaning you have significance, you have something that now is not just random. That's the way evolution systems evolve, is to lower their entropy. Lowering their entropy means increasing their content, increasing their, what's data, what's meaningful, what's significant. So if you have a random field of ones and zeros, the way you evolve is by lowering the entropy of that system and ordering those ones and zeros in such a way that they mean something. They form a pattern, anything, okay? So that's the nature of a evolving information system. Now, evolving information system has to be self-changing. The word evolve implies that it can change, okay? And it changes because it has choices. Those choices determine how it changes. Okay, now that drops us into free will. So we talk about choice, now we have to talk about free will. Okay, free will is much simpler than most philosophers think. Free will, as far as our use of the term, as far as consciousness use, and actually as far as the practical value of free will, is a very simple thing. It's an ability to make a choice, a free choice, out of what I call a selection of choices in your decision space. Free will is personal. It's your free will. Everybody's free will is based on a different size decision space. The size of your reality can be big, or the size of your reality can be small. The size of your decision space can be big and small. What's your decision space? It's all those choices that you have that you know about, that you can make. Now, you may have a much bigger set of choices that are theoretical or that are possible. So all the possible choices, let's say that's this many choices, but just the ones you know about, that's only this many choices. So some choices are outside of your reality, but just the ones you know about make up your decision space. You can decide among those choices. Okay, so if you have an expansive reality, you may have expansive decision set. Now, that's free will is your free choice to decide among the decisions, the choices that you have within your decision space. That's all there is to it. Free will, as it turns out, is absolutely logically necessary for consciousness to exist, and vice versa. You cannot have free will without consciousness. You cannot have consciousness without free will. Those are a logical set. Each one's necessary for the existence of the other. You cannot have an evolving consciousness without choice. The evolution or the choice doesn't mean anything unless it's free. Okay. So those two have to go together. Okay. Now, people sometimes have a problem when I talk about randomness and chance and uncertainty, because if they're computer scientists, randomness means one thing. There's this pure randomness that computer scientists can explain to you that is a little different. When I talk about randomness, I'm talking about choice, choices that make a difference to us. Now, when we make a choice, if we have choices A, B, C, and D, and we go to D, then from there we have a different set of choices than we would have if we had gone to A. Every choice you make sets up a different array of next choices because you're in a different spot than where you were. So you see, this is in a line of choosing. This is how you grow. This is how you evolve, is by the choices that you make. Okay, self-changing systems with a purpose evolve to be more successful. They evolve depending upon their environment. Every environment has conditions. In the physical world, the conditions that say whether you pass or fail is basically survival and ability to procreate. Okay, those are the criteria for successful choices in physical evolution. The conditions for successful choices in the consciousness system is that you lower your entropy. You always are finding more order. You're increasing your content. The value of your content's going up. You're decreasing entropy. Complex interactions produce practical randomness. Okay. Anybody here know what Brownian motion is? Does that ring a bell? Brownian motion? All right, that's if you have a bunch of particles in a box, they all bounce around and hit each other, and because they all bounce around and hit each other, there's no way of telling where any one of them is going to be at any particular time because it's random. I see us in our interaction in this reality as kind of having a social Brownian motion. We bounce into things, we meet people, we have job opportunities, we marry, we have children, all these things do. It's because we just happened to be at that place at that time where we ran into this. It's sort of a social Brownian motion. And there's a lot of randomness in it, and the reason that you're in the career you're in now isn't because you probably always wanted to be whatever it is you do now. It's because you just happened to be at that place where that opportunity was with that credential or whatever to get that particular job, which led to something else, which led to something else, which led to where you are now. And had you been in a different place, that you made a different decision, you'd be somewhere else. If you'd majored in English instead of, physics, you'd be somewhere else. So that's the way it is. We have all these choices, and that's kind of like this Brownian motion. You bump here, which bumps you there, and then you just happen to run into somebody who moves you in that direction, and then some other direction, and we just bump around. And all that bumping around produces lots of choice. We're always getting a whole new array of choices. Every choice we make sets us up with more choices. And that's enough to support free will. That's enough to support a decision space. You see, you have these new choices, and they're constantly changing based on what you do, and you get feedback. All right. Attributes of consciousness. What is consciousness like? What is this data field like? Consciousness is real, it's finite, it's large, complex, self-modifying information system. Okay, it can either evolve or de-evolve. Staying the same is not a good option. I can say it's not an option. Things don't stay the same. Okay, they can't stay the same forever. Now you could say, well, maybe they could just bounce in and around that average point and stay there forever, but it doesn't work that way. The more down you get, the more likely you are to go down further. The more up you get, the more likely you are to go up further. It's an unstable position. It's like balancing something on a needle point. It starts to turn, it goes that way. It's hard to just stay there. It doesn't happen. Eventually it'll either evolve or it'll de-evolve. Okay, individual consciousness evolves toward lower entropy, and I'm going to equate lower entropy with higher quality, more spiritual states. Now I've added a bunch of new words. So lower entropy means a high quality consciousness, and in more common terms, it's a more spiritual consciousness. And that's because the next sub-bullet there is love is the nature of a low entropy consciousness. And a lot of people ask me questions about that. Now, how is it again that you associate low entropy with love? That seems to be a hard one, so we'll do that one again. Okay, let me posit two different groups of beings. One group we'll call utopia, and in that group, in the utopian group, all the beings in this group are going to be caring. It's about other, love, helping. They're all cooperative. It's all that's sort of a mind frame. And in the group called hell, they're all self-centered. It's what about me? It's not about other. And we're going to take these two groups and we'll have equal numbers of both. Let's say we have 10,000 utopians and 10,000 from hell, and we're going to put them in an environment. We're going to put them in this bubble, and they'll have a certain amount of resources and a certain amount of time to do whatever they do with those resources. Okay, it's going to be a sociological experiment. So we do that, and what would you expect to happen? Well, the group that is based on cooperation and helping each other out is going to eventually optimize themselves within their resources. The whole group will end up optimizing. Those who have good talents will use those talents, and those that maybe are just labor, they will be the labor. Everybody will work together. And the group in hell, what are they going to do? Well, they're going to fight with each other. They're going to try to steal each other's stuff. Each one wants to know what's in it for them before they give anything. How much am I going to get? And if they're not going to get more than they give, they're not going to do it. What happens there is eventually they form up into power groups. Somebody who's better at getting will get more, and the more power they have, the more power they can get. The more you got, the more it's easier to get, and you will end up with power groups. But it won't be just one, it'll probably be several, and those several will all fight with each other. War. So that's what happens in hell. Well, where do we live? Do we live in utopia or do we live in hell? Kind of sounds like us, right? Well, because consciousness is about interaction. Consciousness is about relationship. Consciousness is individuated units of consciousness like us. We're interacting with each other. Okay, that's what it's all about. It's our interactions. So which of these two interactions tend toward higher entropy and which tend toward lower entropy? You see the connection? The lower entropy, which means order, right? Building, structure, that's the group that's cooperative. They build. The other one's based on fear, the opposite of love, and they're tearing things apart. Somebody gets something, somebody else wants to take it away from them. It's all about them. That's back to the law of the jungle, right? You don't help people, you use people. And that doesn't get very far. That's kind of a mean place to live. So we can associate low entropy consciousness with love, because love is the nature of low entropy consciousness. Now we have a definition. Now we have a technical definition for love. Love is the nature of a low entropy consciousness. Okay. So now we also have an idea of what it is we're doing here. We are becoming love. We're supposed to evolve our consciousness. Evolving our consciousness means becoming more love-like. De-evolving our consciousness becomes more fear-motivated. Okay, so that kind of tells us where we are in this process. Any process that lowers the system's entropy, builds, creates a more organized, profitable set of relationships and interactions that benefit the whole system. That's moving in the, that's moving in a positive evolution direction. Processes that raise system entropy, pull things apart, disintegrate, create less organization and a less profitable whole system. That's the definition of de-evolving. So love, no fear, no ego, optimizes positive communication, interaction, and relationship between people. Fear isolates, inhibits, and fractures positive communication, interaction, and relationships between subsets of consciousness. Okay, so that's the connection there. All right. Now, the origins of consciousness. Where does this consciousness system come from? We have to make an assumption here, because just like Darwin's theory of evolution, Darwin doesn't know where that first cell came from. He just takes that cell and starts talking about evolution and how that cell would have naturally become more organized, broken into several cells, because multiple cells are more survivable than one, and then those several cells would have multiplied into cells that were cooperative. So you had the locomotion part and the digestion part and the sensor part. So they find that you lower entropy with organization. You see how we're getting through more organization, we have more cells, they're being cooperative with each other, they're working as a system, and as you do that and you build up that complexity, you're lowering your entropy. You got more structure, more order, lowers the entropy, and the organism, the thing that you're getting, is more adaptable, okay, more functional, because now it's a group that are all working together. They're all working for each other. So your cells of your body are sort of like utopia. They're all working together for one, for one cause. Okay, within the origins of consciousness work the same way. You start with potential energy that could just recognize, was self-aware enough to know that there was a difference between being this way and being that way. That's two states. It's a binary, 1 and a 0. That's all, something that had some self-awareness. Now, what is this something and where did it come from? I have no idea. There are limits to knowledge, and when we come back from lunch, we'll have a slide about the limits of knowledge, but we don't know. So what makes Darwin's theory a good theory? Well, not because it's based on where did the first cell come from, it doesn't know. What makes Darwin's theory a good theory is that it fits all the data. If you look at all the data of all the creatures and look at the embryos and look at how they develop and structures and so on, you got a lot of data there, and his theory just fits the data. Why are some birds yellow and some birds green and so on, and you can just see, well, here's how it evolved. It's connection with their environment. Well, it's the same with this big toe. I don't know where this first potential energy that could differentiate state 1 from state 2 of itself, but if you start from there and go, your theory can fit all the data, all the physics and all the metaphysics. So that's basically, we're doing the same way that Darwin did. So here's the rule. So here's the way it goes. You have this system, it can define two states, this and that. Well, if it can define two states, then it can define more than two states. It's like the cells over here in the Darwin world splitting, right? So now it can make more cells. So it can find this state, another state, and another state. And pretty soon it can populate lots of ones and zeros. Well, if it's got lots of ones and zeros, it can start making information, which may be just patterns, something. It's evolving. This is not intelligent. It's not bright. It's like at the same level as a little clump of cells over here in the primordial soup in Darwin's world. But it evolves, and it grows, and it splits and becomes more complex. And its whole purpose isn't to survive and procreate. Its purpose is to lower entropy. What's that mean? Create more order. Find information. Have that information have meaning. Eventually, it gets to the point where it can divide chunks of itself into separate entities and interact with itself. Okay, why would it want to do that? Because just interacting, just one thing, one monolithic thing interacting with itself is limited in the amount of novelty, in the amount of creativity, in the amount of, lowering its entropy, the amount of structure. It's limited in its complexity. If it can break itself into 100 pieces and have all those 100 pieces interact with each other with free will, they can do whatever they can do within their own little decision space, then suddenly the amount of novelty, the amount of opportunity for change grows up immensely. So you see, that's where we get this consciousness, the idea of consciousness from. So we have you have discovery of this and that, goes to self-modification, you duplicate, you discovers the synergy of interaction, patterns, sequences, patterns of patterns. This thing evolves, and eventually it evolves to what we have now, larger consciousness system that can create virtual realities for chunks of itself to experience so that they can lower their entropy. And since they're a part of the whole system lowers its entropy. So we're a piece of that process. Okay, so that's how that works.